Assalamualaikum and hi there. Today we will continue with our chapter 5 with chapter 6 on discrete probability distribution. Starting with chapter 5, the emphasis changes. We begin examining something that would probably happen. We note that this facet of statistics is called statistical inference. The objective is to make inferences or statements about a population based on a number of observations, called a sample selected from the population. In chapter 5 also, we state that a probability is a value between 0 and 1 inclusive, and we examine how probabilities can be combined using rules of addition and multiplication. So in this chapter, we will begin the study of probability distribution. A probability distribution gives the entire range of values that can occur based on an experiment. A probability distribution is similar to a relative frequency distribution. Again, a probability distribution is similar to a relative frequency distribution. However, instead of describing the past, it describes a likely future event. For example, a drug manufacturer may claim a treatment will cause weight loss for 80% of the population. A consumer protection agency may test the treatment on a sample of 6 people. If the manufacturer's claim is true, it is almost impossible to have an outcome where no one in the sample loses weight, and it is most likely that 5 out of the 6 do lose weight. In this chapter, chapter 6, we discuss the mean, variance, and standard deviation of a probability distribution. We will also discuss 3 frequently occurring probability distributions: the binomial, hypergeometry, and Poisson distribution. Please remember, this chapter 6 refers to your reference book, and according to the syllabus, this chapter will represent the chapter 3. Okay. Now look at our learning objective for this chapter. There are 7 learning objectives for this chapter. Learning objective 1, to identify the characteristics of a probability distribution. Learning objective 2, distinguish between discrete and continuous random variable. Learning objective 3, compute the mean of a probability distribution. Learning objective 4, compute the variance and standard deviation of a probability distribution. Learning objective 5, describe and compute probabilities for a binomial distribution. Learning objective 6, describe and compute probabilities for a hypergeometric distribution. And lastly, learning objective 7, describe and compute probabilities for a Poisson distribution. Let's begin with probability distribution. What is a probability distribution? A probability distribution shows the possible outcomes of an experiment and the probability of each of these outcomes. So according to your reference book, probability distribution is a listing of all the outcomes of an experiment and the probability associated with each outcome. How can we generate a probability distribution? The following example will explain. Suppose we are interested in the number of heads showing face up on 3 tosses of a coin. This is the experiment. The possible results are 0 heads, 1 head, 2 heads and 3 heads. The question is, what is the probability distribution for the number of heads? There are 8 possible outcomes. A tail might appear face up on the first toss, another tail on the second toss, and another tail on the third toss of the coin. Or we might get a tail, and head in that order. We use the multiplication formula for counting outcomes. There are 2 multiply 2 multiply 2, or 8 possible results. Before we continue, let us look at characteristics of a probability distribution. The major characteristics of a probability distributions are: number 1, the probability of a particular outcome is between 0 and 1 inclusive. Second, the outcomes are mutually exclusive events. And third, the list is exhaustive. So, the sum of the probabilities of the various events is equal to 1. Now, continue with our previous example on probability distribution. This experiment, toss a coin 3 times, observe the number of heads. The possible results are 0 heads, 1 head, 2 heads, and 3 heads. So we want to calculate what is the probability distribution for the number of heads. The probability distribution of number of heads observed in these 3 tosses of a coin. Note that the outcome 0 heads occurred only once. 1 head occurred 3 times, 2 heads occurred 3 times, and the outcome 3 heads occurred only once. That is, 0 heads happened 1 out of 8 times. Thus, the probability of 0 heads is 1/8. The probability of 1 head is 3/8, and so on. Because one of these outcomes must happen, the total of the probabilities of all possible events is 1. Next to the table, there is a chart. The chart presents graphical presentation of the number of heads resulting from 3 tosses of a coin and the corresponding probability. You can see here the chart of the probability distribution of number of heads observed in 3 tosses of a coin. Now I will introduce you to random variables. In any experiment of chance, the outcomes occur randomly, so it is often called a random variable. For example, rolling a single die is an experiment. Any one of 6 possible outcomes can occur. Some experiments result in outcomes that are quantitative, such as dollars, weight, or number of children, and others result in qualitative outcome, such as color or religious preference. Each value of the random variable is associated with a probability to indicate the chance of a particular outcome. So, to conclude, Random variable is a quantity resulting from an experiment that, by chance, can assume different values. This diagram illustrates the term experiment, outcome, event, and random variable. First, for the experiment, where a coin is tossed 3 times, there are 8 possible outcomes. TTT, TTH, THT, HTT, THH, HTH, HHT, and HHH. In this experiment, we are interested in the event that one head occurs in the 3 tosses. The random variable is the number of heads. In terms of probability, we want to know the probability of the event that the random variable equals 1. Now we will distinguish between discrete and continuous random variable. There are 2 types of random variables. The first one is discrete random variable. Discrete random variable is a random variable that can assume only certain clearly separated values. It is usually the result of counting something. A continuous random variable can assume an infinite number of values within a given range. It is usually the result of some type of measurement. Now we will look one by one. Discrete random variable. Examples: the number of students in a class. The number of children in a family. The number of cars entering a car wash in an hour. Number of home mortgage approved by Coastal Federal Bank last week. Continuous random variables examples: the length of each song on the latest Teen Macro album, the weight of each student in this class, the temperature outside as you are reading this book, the amount of money earned by each of the more than 750 players currently on Major League Baseball team rosters. Okay, now we will continue with the computation, the mean of a probability distribution. The mean is a typical value used to represent the central location of a probability distribution. The mean of a probability distribution is also referred to as its expected value. It is a weighted average where the possible values of a random variable are weighted by their corresponding probabilities of occurrence. The mean of a discrete probability distribution is computed by the formula mu equal to sum of x px, where px is the probability of a particular value x. In other words, multiply each x value by its probability of occurrence and then add these products. Now we will look at example of mean, variance and standard deviation of a probability distribution. John Ratsdale sells new cars for Pelican Ford. John usually sells the largest numbers of cars on Saturday. He has developed the following probability distribution for the number of cars he expects to sell on a particular Saturday. Okay, from here you can see number of cars sold x 0, 1, 2, 3, 4. The probability of x P0 is 0.1, P1 is 0.2, P2 is 0.3, P3 is 0.3 and P4 is 0.1. The total is 1. The mean number of cars sold is computed by weighting the number of cars sold by the probability of selling that number and adding or summing the products. So using the formula, you will get the mu equal to 2.1. The calculations are summarized in the table. You can see here from the table. The variance and standard deviation of a probability distribution. As noted, the mean is a typical value used to summarize a discrete probability distribution. However, it does not describe the amount of spread or variation in a distribution. The variance does this. Measures the amount of spread in a distribution. The computational steps are: the first one is subtract the mean from each value and square this difference. And then multiply each squared difference by its probability. And then sum the resulting products to arrive at the variance. The standard deviation is found by taking the positive square root of the variance. Okay, just refer to our previous example. From that example, we can calculate the variance and standard deviation. Use the formula of variance and standard deviation. You will get the variance equal to 1.29 and the square root of 1.29 is the standard deviation, where it is 1.136. So, how do we interpret a standard deviation of 1.136 cars? If salesperson also sold a mean of 2.1 cars on Saturdays and the standard deviation in her sales was 1.91 cars, we would conclude that there is more variability in the Saturday sales of this sale than in those of Mr. Ragsdale, because 1.91 is greater than 1.136. Okay, now the first type of probability distribution is binomial probability distribution. This distribution is a widely occurring discrete probability distribution. One characteristic of a binomial probability distribution is that there are only two possible outcomes on a particular trial of an experiment. For example, the statement in a true-false question is either true or false. The outcomes are mutually exclusive, meaning that the answer to a true or false question cannot be both true and false at the same time. The random variable is the result of counts. That is, we count the number of successes in the total number of trials. We flip a fair coin 5 times and count the number of times a head appears. We select 10 workers and count the number who are over 50 years of age. Or we select 20 boxes of Kellogg's Raisin Bran and count the number that weigh more than the amount indicated on the package. The final characteristic of a binomial probability distribution is that each trial is independent of any other trial. Independent means that there is no pattern to the trials. The outcome of a particular trial does not affect the outcome of any other trial. Binomial probability experiment. An outcome on each trial of an experiment is classified into one of two mutually exclusive categories, whether it is a success or a failure. The second one is the random variable counts the number of successes in a fixed number of trials. The probability of success and failure stay the same for each trial. And lastly, the trials are independent, meaning that the outcome of one trial does not affect the outcome of any other trial. How is a binomial probability computed? To construct a particular binomial probability, we use number 1, the number of trials, and number 2, the probability of success on each trial. For example, If an examination at the conclusion of a management seminar consists of 20 multiple choice questions, the number of tries is 20. If each question has 5 choices and only one choice is correct, the probability of success on each trial is 0.2. Thus, the probability is 0.2 that a person with no knowledge of the subject matter will guess the answer to a question correctly. So, the conditions of the binomial distribution just noted are met. A binomial probability formula is Px and Cx pi x 1 minus pi n minus x, where C denotes a combination, n is the number of trials, x is the random variable defined as the number of successes, pi is the probability of success on each trial. We use the Greek letter pi to denote a binomial population parameter. Do not confuse it with the mathematical constant, whereas pi is 3.1416. Example of binomial probability. There are 5 flights daily from Pittsburgh via US Airways into the Bradford Regional Airport in Bradford, Pennsylvania. Suppose the probability that any flight arrives late is 0.2. What is the probability that none of the flights are late today? What is the probability that exactly one of the flights is late today? So for the first question, we can use the formula for binomial probability. The probability that a particular flight is late is 0.2. So let pi equal to 0.2. There are 5 flights, so n equal to 5. And x, the random variable, refers to the number of successes. In this case, a success is a flight that arrived late. Because there are no late arrivals, x equal to 0. So, Px equal to 0. When you compute, you will get the answer of 0.3277. For the probability that exactly one of the flight is late today, you can refer to your reference book. So this is the slide that captured from Excel to show you how you can use Excel to compute and to graph the binomial probability. Yeah, now show you what is the probability that none of the flights are late today. The mean and the variance of a binomial distribution can be computed in a shortcut fashion by below formulas. Mean of binomial distribution, mu equal to n pi. Variance of a binomial distribution, sigma squared equal to n pi multiply 1 minus pi. Example. For the example regarding the number of late flights, recall that pi equal to 0.2 and n equal to 5. So what is the average number of late flights? What is the variance of the number of late flights? So using the previous formula, you will get the mu is equal to 1 and the variance is equal to 0.8. The mean of 1 and the variance of 0.8 can be verified from formulas. The probability distribution from the Excel output on the example and the details of the calculation are shown in this table. And from this slide, you can see another solution or another formula to compute the mean and variance. You can also compute the mean using this formula, sigma x px, and variance sigma x minus mu squared multiplied by px. Binomial probability tables. Formula can be used to build a binomial probability distribution for any value of n and pi. However, for a larger n, the calculation takes more time. For convenience, the table 6.2 is used. Another example, 5% of the worm gears produced by an automatic high-speed cutter bell milling machine are defective. What is the probability that out of 6 gears selected at random, none will be defective? Exactly 1, exactly 2, exactly 3, exactly 4, exactly 5, exactly 6 out of 6. The binomial conditions are met. Okay, the first one, there are only 2 possible outcomes. A particular gear is either defective or acceptable. And then there is a fixed number of tries. It is 6. There is a constant probability of success. It is 0.05 and the tries are independent. Refer to table 6.2 for the probability of exactly 0 defective gears. Go down the left margin to an x of 0. Now, move horizontally to the column headed by a pi of 0.05 to find the probability. It is 0.735. The probability of exactly 1 defective in a sample of 6 worm gears is 0.232. The complete binomial probability distribution for n equal to 6 and pi equal to 0.05 is 0.735 for P0, P1 equal to 0.232, P2 equal to 0.031 and P3 equal to 0.02. P4 equal to 0.00, P5 equal to 0.00 and P6 equal to 0.00. Of course, there is a slight chance of getting exactly 5 defective gears out of 6 random selection. It is 0.0000178 found by inserting the appropriate values in the binomial formula. For 6 out of the 6, the exact probability is 0.000000016. Thus, the probability is very small that 5 or 6 defective gears will be selected in a sample of 6. Several additional points should be made regarding the binomial probability distribution. Look at this graph representing the binomial probability distribution for a pi of 0.1 and an n of 7, 12, 20 and 40. Several additional points should be made regarding the binomial probability distribution. If n remains the same but pi increases from 0.05 to 0.95, the shape of the distribution changes. Look at the table or chart 6.2. The distribution for a pi of 0.05 is positively skewed. As pi approaches 0.5, the distribution becomes symmetrical. As pi goes beyond 0.5 and moves towards 0.95, the probability distribution becomes negatively skewed. If pi, the probability of success, remains the same but n becomes larger, the shape of the binomial distribution becomes more symmetrical. Chart 6.3 shows a situation where pi remains constant at 0.1 but n increases from 7 to 40. Binomial probability distribution. We may wish to know the probability of correctly guessing the answers to 6 or more true-false questions out of 10, or we may be interested in the probability of selecting less than 2 defectives at random from production during the previous hour. In these cases, we need cumulative frequency distribution similar to the ones developed in previous chapter 2. This example will illustrate. A study by the Illinois Department of Transportation concluded that 76.2% of front seat occupants use seat belt. That means that both occupants of the front seat were using their seat belt. Suppose we decide to compare that information with current usage. We select a sample of 12 vehicles. What is the probability the front seat occupants in exactly 7 of the 12 vehicles are wearing seat belt? To find the likelihood the occupants of exactly 7 of the sampled vehicles are wearing seat belt, we use previous formula. In this case, n equal to 12 and pi equal to 0.762. You will get 0.0902. So we conclude the likelihood that the occupants of exactly 7 of the 12 sampled vehicles will be wearing their seat belt is about 9%. Okay. Next, what is the probability the front seat occupants in at least 7 of the 12 vehicles are wearing seat belt? To find the probability that the occupants in 7 or more of the vehicles will be wearing seat belt, we use previous formula as well as the special rule of addition from the previous chapter. Because the events are mutually exclusive, meaning that a particular sample of 12 vehicles cannot have both a total of 7 and a total of 8 vehicles where the occupants are wearing seat belt, we find the probability of 7 vehicles where the occupants are wearing seat belt, the probability of 8, and so on, up to the probability that occupants of all 12 sample vehicles are wearing seat belt. The probability of each of these outcomes is then total. So, you will get 0.9562. The probability of selecting 12 cars and finding that the occupants of 7 or more vehicles were wearing seat belt is 0.9562. This information is shown in the calculation. And also on the following Excel spreadsheet. There is a slight difference in the software answer due to rounding. The Excel commands are similar to those detailed in the software commands. The sum of probabilities for 7 or more successes is 0.9563. Okay. The second type of probability distribution is hypergeometric. For the binomial distribution to be applied, the probability of a success must stay the same for each try. For example, the probability of guessing the correct answer to a true or false question is 0.5. This probability remains the same for each question on an examination. Likewise, suppose that 40% of the registered voters in a precinct are Republicans. If 27 registered voters are selected at random, the probability of choosing a Republican on the first selection is 0.4. The chance of choosing a Republican on the next selection is also 0.4. Assuming that the sampling is done with replacement, meaning that the person selected is put back in the population before the next person is selected. Most sampling, however, is done without replacement. Thus, if the population is small, the probability for each observation will change. For example, if the population consists of 20 items, the probability of selecting a particular item from that population is 1/20. If the sampling is done without replacement, after the first selection there are only 19 items remaining. The probability of selecting a particular item on the second selection is only 1/19. For the third selection, the probability is 1/18, and so on. This assumes that the population is finite, that is, the number in the population is known and relatively small in number. Because the probability of success does not remain the same from trial to trial when sampling is from a relatively small population without replacement, the binomial distribution should not be used. Instead, the hypergeometric distribution is applied. Therefore, if a sample is selected from a finite population without replacement, and if the size of the sample N is more than 5% of the size of the population N, then the hypergeometric distribution is used to determine the probability of a specified number of successes or failure. It is especially appropriate when the size of the population is small. In summary, a hypergeometric probability distribution has this characteristic. An outcome on each trial of an experiment is classified into one of two mutually exclusive categories, a success or a failure. The probability of success and failure changes from trial to trial. The trials are not independent, meaning that the outcome of one trial affects the outcome of any other trial. Note, use hypergeometric distribution if experiment is binomial, but sampling is without replacement from a finite population where small n divided by big N is more than 0.05. Small n is equal to the number of sample and big N equal to the number of population or the size of the population. The formula for the hypergeometric distribution is Px equal to SCx multiply n minus SCn minus x divided by NCn, where n is the size of the population, s is the number of successes in the population, x is the number of successes in the sample. It may be 0, 1, 2, 3 and so on. N is the size of the sample or the number of tries, and C is the symbol for a combination. So now we look at the example. Playtime Toys Incorporation employs 50 people in the assembly department. 40 of the employees belong to a union and 10 do not. 5 employees are selected at random to form a committee to meet with management regarding shift starting times. What is the probability that 4 of the 5 selected for the committee belong to a union? The population in this case is the 50 assembly department employees. An employee can be selected for the committee only once. Hence, the sampling is done without replacement. Thus, the probability of selecting a union employee, for example, changes from one trial to the next. The hypergeometric distribution is appropriate for determining the probability. So, in this problem, here's what's given. N equal to 50, number of employees, S equal to 40, number of union employees, X equal to 4, number of union employees selected, N equal to 5, number of employees selected. We wish to find the probability 4 of the 5 committee members belong to a union. So using the formula, you will get 0.431. Thus, the probability of selecting 5 assembly workers at random from the 50 workers and finding 4 of the 5 are union members is 0.431. Now, the last type of probability distribution is Poisson. The Poisson probability distribution describes the number of times some event occurs during a specified interval. The interval may be time, distance, area, or volume. The distribution is based on two assumptions. The first assumption is that the probability is proportional to the length of the interval. The second assumption is that the intervals are independent. To put it another way, the longer the interval, the larger the probability, and the number of occurrences in the one interval does not affect the other intervals. This distribution is also a limiting form of the binomial distribution when the probability of success is very small and n is large. The Poisson probability distribution is characterized by the number of times an event happens during some interval or continuum. Examples include the number of misspelled words per page in a newspaper, the number of calls per hour received by Dyson Vacuum Cleaner Company, the number of vehicles sold per day at Hyatt Buick GMC in Durham, North Carolina, and the number of goals scored in a college soccer game. The Poisson distribution can be described mathematically using the formula below, where mu is the mean number of occurrences or successes in a particular interval, E is the constant 2.71828 based on the Neperian logarithmic system, X is the number of occurrences or successes, Px is the probability for a specified value of X. The mean number of successes mu can be determined by n pi, where n is the total number of tries and pi the probability of success. Yes, again, the mean number of successes mu can be determined in Poisson situation by n pi, where n is the number of tries and pi the probability of a success. The variance of the Poisson distribution is also equal to n pi. Poisson probability distribution example. Baggage is rarely lost by Northwest Airlines. Suppose a random sample of 1,000 flights shows a total of 300 bags were lost. Thus, the arithmetic mean number of lost bags per flight is 0.3, where 300 divided by 1,000. If the number of lost bags per flight follows a Poisson distribution with mu equal to 0.3, find the probability of not losing any bags. So, using the formula, P0 equal to 0.7408. That is the probability of no lost bag. Recall from the previous illustration that the number of lost bags follows a Poisson distribution with a mean of 0.3. By using your appendix B.5 in your reference book, you can find the probability that no bags will be lost on a particular flight. So what is the probability no bag will be lost on a particular flight? To find the probability of no lost bag, locate the column headed 0.3 and read down that column to the row labeled 0. The probability is 0.7408. That is the probability of no lost bag. More about the Poisson probability distribution. The Poisson probability distribution is always positively skewed, and the random variable has no specific upper limit. The Poisson distribution for the lost bags illustration where mu equal to 0.3 is highly skewed. As mu becomes larger, the Poisson distribution becomes more symmetrical. Look at the chart below. The chart below shows the distribution of the number of transmission services, muffler replacement, and oil changes per day at one of the auto shop. They follow Poisson distribution with means of 0.7, 2.0, and 6.0 respectively. In summary, the Poisson distribution is actually a family of discrete distribution. All that is needed to construct a Poisson probability distribution is the mean number of defects, errors, and so on, designated as mu. Okay, this is the end of the chapter 6. So, thank you for listening to me, and we will see you again in our e-learning for chapter 7. Thank you very much.